Thank you. Before I start on the subject of this last lecture proper, let me put up a slide from a previous lecture, and it is the one, if I may have it, of the earthquake distribution under Japan, but typically in many parts of the world. And after that lecture, one of you came up and pointed out to me that these two signs, less than should have been the other way around, and greater than should have been that way around. Is he here today? Where is he? Well, just stand up. Well, may I say that that slide actually comes from a book where presumably many readers might have seen it, and I've used it in lectures not only here but in other countries too, and either the audiences have been too polite or, I suspect, not anything like as awake as you are, and congratulations for spotting it. The next slide also is a slight carryover from the last lecture, because, which remember, we finished by talking about infrared. And I had mentioned that quite often in the natural world you come across a case where some animal has used what you've just discovered already. And in this particular case, these rather nasty animals, the rattlesnakes, turn out to have infrared detectors. You'll have to read the details in the book, but it's another very interesting case. You see, a snake has no external ears, nostrils and eyes, and all this class of snake, the rattlesnakes and several other snakes, but not all of them, have these two pits, one on either side of the head, there and there. And they turn out to have a membrane across the bottom, which is an infrared surface detecting, and coupled in to that part of the rattlesnake's brain, which also decodes the signals from its eyes. And this turns out to be the justification for an old cowboy story that rattlesnakes could strike in the dark, because they really can strike in the dark. If they get something like your hand within a foot or two, they can strike unerringly in the dark. And one other carryover from a previous lecture, which is in the next slide, we talked about the Doppler effect, and I just had time to mention that irrespective of the distance, if you can pick up waves from the other body, then you can see the wavelengths shifted, particularly if it's going away from you, they will be extended, and of course coming towards you, as we saw, they would be compressed. And to give you an idea of the range of that method of measuring velocity, the furthest bodies that we can see in the sky, these galaxies, which we think are, in some cases, very like our own, when we look at the spectrum, there are broad lines in it which can be recognized, and the further away they are, the more the spectra seem to be moved over towards the red, the longer waves, giving us the impression at least that the galaxies are all receding from us. And the biggest velocities detected by this method are of the order of 100,000 miles a second, roughly half the velocity of light. And by contrast, the effect can also be used to measure very small velocities. I was very surprised to find recently that in the botany department in my own university, Dr. Richard Johnson had been using exactly the same effect, but now through a microscope rather than a telescope, looking at the particles in sieve tubes, the starch particles in sieve tubes in plants, and there, by measuring the Doppler effect on the laser light, it's a very tiny effect then, but because the precision of frequency of light coming out of a laser, it can nevertheless be detected. And there, as opposed to 100,000 miles a second, 1 micron a second can be detected quite easily. Well, I hope this will add interest to what undoubtedly you will have to look at, and is certainly one of the most interesting phenomena in the whole of physical optics, the Doppler effect. Now, in this last lecture, I want to really get to the subject. Remember, we started roughly with Magna Carta, and we almost promised by title that we would end with microchips. And for that, I want to give you just a very brief sketch of how microcircuits are made. Electronics, of course, started and developed for at least 50 years with refinements of the thermionic valve, which was invented in 1907. And here are some of them, including a very favourite valve of World War II, the EF-50, which went into all our radar sets, and that was like that. Now, just before World War II, or the years before World War II, some of us had seen the advantage of making things small. And I myself tried to make what might have been some of the very first integrated circuits around 1935, where one could take advantage now of the fact that one could make a vacuum. And as a result of that, if you had a really good vacuum and you had, say, a filament, rather like the filament in an ordinary incandescent tungsten lamp, and you put a little piece of metal into it and it melted, it would evaporate, and the metal would stream out across the vacuum and condense on any surface in the way. Most of our mirrors today are made that way using aluminium. And the point was you could put different metals in. So I could put in bismuth or antimony, and the junction of the two would make a detector of infrared radiation. But the best I could do probably was lines about 0.5 millimeter wide. And when, after the war, computers had now been invented, they depended on valves like this, and the earliest computers had an enormous number of valves in them. Because of the heat in their filaments, they got very hot, they took a lot of current, and of course you couldn't get a great many into a given volume. And so the incentive to make what were called integrated circuits by these techniques that we'd just begun to use before World War II really began to take off. And with the obvious prizes that were to be had in more compact and faster electronic circuits, partly because if the smaller you can make the components, the shorter would be the leads between, the shorter time it would take the electrical signals to pass from one component to another, and therefore the faster the whole device would work. And the prospects of making fast, compact computers using relatively low power, of course, was a very encouraging one to try to pursue. And following the invention of the transistor around 1948, it became possible to conceive of integrated circuits where one didn't use devices like this at all, but instead used the properties of semiconductors like germanium and latterly, and more importantly, silicon. And the process gradually developed, first of all, of making germanium and silicon crystals, which were very good semiconductors. And then, for example, taking a slice of silicon, a thin slice of silicon which had been grown as a crystal, and then by means of what you might think of as stencils or masks, you put these down. This is highly magnified. This is the technique of perhaps 10, 15 years ago. And already, you see, it had reached the stage where you could, if you got the right kind of mask or stencil, you could duplicate a pattern. And very often computers want many samples or members of the same kind of circuit. And so you could make what we called an integrated circuit like this, where one could have a good conductor for the leads, one could have semiconductors or very thin films making high resistances, and you could actually put on all the electrodes for the making of a transistor. And the technology, you see, had then reached the stage of, well, this is roughly 0.15 of an inch, roughly a 60th of an inch, or shall we say, around a third of a millimeter, like that. And each of these complete units is of the order of a third of a millimeter square. Well, technology has advanced since then, and now, if necessary, instead of using a crystal of silicon and slicing it, one can work with thinner materials or thinner silicon layers too. And one of the good bases for these things is, and here you have a thin slice here, and all the microcircuit examples I have here have been provided by the kindness of our General Electric company. And here you see a slice of sapphire. Sapphire, as you know, is a gem, but it can now be made on a large scale as a crystal, and it's sawn with diamond saws into very thin slices, so that makes the basic support. It's nothing but a support for the microcircuitry that one hopes to put on it. And now, of course, the stencils are becoming extremely complex and very and minute in their detail. At an earlier stage, one could see them quite easily. Again, this is the technique of perhaps 15 years ago. And here on the microscope, one could actually see the stencil and check it. And the precision with which the stencils have to be made, and still more the precision with which one after another have to be put down on the same very flat surface. You've got to be able to make these surfaces very flat indeed. The stencils or marks have got to come down very near to the surface indeed. And they all have to go on one after another, putting on the various layers of material by techniques which really deserve. One day you ought to have a whole Royal Institution series of lecture discourses at Christmas on the microchip itself, because I can merely indicate to you today the precision that's involved and the stage that techniques have reached, and just a brief indication of how much further they might go. And so I shall concern myself entirely with the precision of and delicacy of manufacture. Again, this is, you see a big advance on the next picture, because this is what is known as a delay line used in radar devices for comparing one radar picture with the one taken the next time round to see if all the echoes are in the same place. If they're not, you know that there's a moving target there and it's not a hill or tree or something like that. And you have to delay the radar signals from the previous picture, previous scan, by sending them down here, which is what we call a delay line, and using them to cancel out any echoes which are exactly where they were before. And the interesting thing from the point of view of the scale now is that the overlap, you can see, I hope, that some are mauver and browner than others. Well, that region of overlap, which is just a bit thicker than this rod, is 3 microns. So already, you see, one was beginning to get to the position where microns not merely mattered, but were in fact predominant. And so a lot of technology of making the masks and putting them into registration has been pursued in several countries, of course, because the prize, again, is both military but primarily commercial in the microchip. And when there's a lot of money to be had from something, it sharpens people's intentions marvelously. And an enormous amount of painstaking and ingenious technology has been the result. And again, we have some specimens here. And onto the silicon slice, onto the sapphire slice, sorry, in these cases, has been evaporated by the same technique through a vacuum, a very thin layer of the element silicon. Silicon is a very common element. It's one of the main elements in sand, of course, with the other oxygen being the other. But it has to be made very purely, and there, partly by the efforts of physicists and partly by chemists, very pure materials are available. And the purity has to be better perhaps sometimes than one stray element in 1,000 million. So there's some very fine chemical technology at the basis of this too. But when you've got all the materials, then it comes to a question of making the masks. And you can't make the masks usually on the tiny scale that they're going to be used, because many of the connections now are 1 micron wide or less. Remember, that's about 1/50th of the diameter of a hair. And so what is usually done is a replica of the mask on at least 10 times the size is made. And if that can be, yes, that's visible on the cameras now. That is one typical mask, and many might be used in making one microcircuit, and it has to be reduced typically by optical techniques through almost using a microscope the wrong way round, in order to make little areas of mask 1/10 the size of that. And then the disc with the silicon on it would be treated by all the appropriate techniques through such a mask, and by stepping from one to the next one, and this has to be done all over the disc, you will find each one of these, if you could look at through a microscope, which we will now do, it is a complete, it's not just a single circuit, it is a complete system which will, its purpose, let me tell you, is it nice and clear on the screen now? Then if that is coming through all right, you should be able to see, now it is, you see, some of, just part of that, part of one of those circuits, and there across it is stretched a specimen of human hair, and you can see how very much finer the detail is than the thickness of a human hair. You can also, actually the silicon is so thin that you can see through it if necessary, and it gives you some idea of how they're made. In large numbers, you see, the slices are then cut up into their individual components, and of course the biggest problem of all is to connect them to the outside world, or at least one of the big problems. Here is a typical example, you see. There is part of the microcircuitry. You've got to make contacts, and so one has to also fabricate them through the same mask techniques, and to have convenient sized squares onto which you can make these connections, which are typically gold wire, just about the thickness of a human hair, which is pushed down and pressure welded into contact. And of course all those contacts have to be perfectly made. These very slender wires are then taken out to much more solid contacts onto which you can make connections as you please, and the whole thing is then mounted up, and again under the microscope we will see one of those chips, as they're called, now mounted up. And can we move it over, Bill, so that the leads can be seen? I don't know whether they'll come out very well. I think you can begin to see them up there. Yes, you can see the wires coming off. Well, there you see are quite thin. And in this way, a chip is made. And this particular chip is a multiplier. It will do multiplication sums for you. And its capacity is such that it would take two numbers of up to 50 or 60,000 and multiply them together for you and give you the answer. And it will do that, or any similar sum, 5 million times a second. That is the power of the technique. So you can see how things have gone. And now if we take this same slice and you like to have a guess at how many transistors there are on that slice, I certainly wouldn't have guessed, and I don't imagine many of you would, unless you already knew. It is about 1,350,000 transistors on that single slice. To do that work with even this relatively late developed valve, if we stack them all close together, they would much more than fill the lecture room. Much more than. And what is more, here are also all the other components, because you can make resistances, you can make capacitances, you can make every component of an electronic circuit in this way. And so along with this 1,350,000 million transistors are all the other necessary components as well. Well, I hope that gives you very, very briefly some idea of the challenge to precision of workmanship which has been involved. Here we have another example, just to give a scale, again, of part of an integrated circuit. And here you see the scale can be given by the fact that these holes, or at least these circles here, are just 1 micron in diameter. And you can see the beauty of the work. Now, are there limits to what we can do here? And the answer, of course, is yes. We saw one the other day when I showed you the shadow of a needle. And round the shadow of the needle, you could see diffraction occurring. And so you can't have the mask very far away from the slice, and that's why it has to be so very close, because the light would start to bend round and blur the image. And so, again, since light waves are quite large, you see, by comparison with the dimensions that we're looking at least they're of the same order, there is a premium on being able to use much shorter wavelengths so that the radiation would effectively travel in straighter lines, be diffracted less. And so we're beginning to find the use of X-rays and X-ray lithography, as it's called, in the fabrication of microcircuits. And of course, the other physical quantity or object which has correspondingly short wavelengths to X-rays are electron beams. And so we're beginning to find electron beams, which of course can be very conveniently controlled by computers, being made to etch surfaces, and we can see examples. I'm not quite sure whether this is electron beam or the ultimate in optical, but you can see here this scale is roughly 4 microns, 3 microns, 2 microns, and you can see the beauty of and accuracy of the structures. You couldn't get these photographs with an optical microscope. You've got to go to the electron microscope because of the sharper detail it resolves to see that really micron spacing with considerable depth have been achieved. The next slide shows the whole of one such chip, as we've seen mounted up, and you'll see in the eye of a needle. And the X-ray lithography and electron beam lithography represent the next stage in manufacture, which is just about coming in. So devices could be even smaller than the chips we've been looking at. Well, so much for the chip itself, a tremendous achievement. And let us look for a few minutes at some of the results. Now, you have seen some of the results already, in fact, all the time in these lectures. But in particular, those absolutely splendid pictures of the interference fringes from red light, from blue light to green light and back and forwards, the pictures of the Royal Institution with the one component being on the one the other. That was possible because the whole of the image could be stored in a system used by the BBC. And the question comes of how can one store an image, and not only a black and white image, but a coloured image too. And for that, it's necessary to spend a minute or two looking at how one does analyse a picture down into signals which can be processed by the electronics and the picture recreated again at the far end. And to start with, let us just see this picture, a relatively uninspiring and not very colourful picture of a tartan bow. And its interest, particularly here, is not only was it the first colour picture ever taken by photography in the world, but it was first done and shown here in 1861. The colour, to some extent, is false because in those days there was no red sensitive photographic plate, but nevertheless the full principle was really demonstrated in this lecture theatre by James Clerk Maxwell at that time. He had been very interested in colour vision, and the phenomenon on which these pictures depended, he had three of them superimposed, and it's the three volunteers I want, if you'll come out. And what I want is, we'll try and give at least some people a surprise, because I want one of you to take this switch, the red, one of you to take the green, and one of you to take the blue. And we'll have to have lights well down for this. And now, if the red, turn the red one on, like that, you'll see there is a patch of red colour. This almost simulates the first of the demonstrations that Maxwell did. So there we have the red. Now, what will happen if we switch the green on? I think one of the biggest surprises I've ever had, if you switch the green one on, there like that, and you'll see, contrary to what one would think from using paints on paper, the red and the green, where they overlap, give you a yellow. We mentioned this the other day, but there is a better example of it. And the reason is that our eyes analyse colours into three, because we've got three basic sensitive receptors in type in our eye. And when we see truly a yellow, it partly activates the red and partly the green in our eyes. And our brain says, I know what that is, it's yellow. And you can trick our brains by giving not a true yellow, but what's called a synthetic yellow, by the red and the green overlapping. And now if the blue one is switched in, like that, you can see that in the middle now, where the red and the green have already overlapped to give a yellow, if you bring in the blue, you get what is very nearly a white. Well, thank you very much for that demonstration. We can now switch off, if we would. That one's off, like that. And Maxwell showed that you could represent any colour by the mixtures of these three. And he constructed what is known as the colour triangle. It's a very, of course, not a terribly good picture, but it does at least give the idea, the colours should be much purer than this really, that if you take roughly a triangle and make the apex here red, that apex green, and that one blue, mixed in the right proportions of colour, you get a white, and going that way, you get a gradually increasing red through pink, and so forth, the seeming yellows here, and the greens up here, and so forth. And you can specify then any colour by the length of the perpendiculars from here down to here, here to there, and here to here. And so if you can effectively measure those lengths, you can say we have a measure of the colour and the degree of saturation. Now, how can one get that into a system which electronics can handle? And the next slide gives you perhaps a very rough idea. Supposing one was scanning along a television line, and in any one colour, the distribution was like that as you went along the line. You can measure it in ordinary units up this way. Now, you can code it on the binary scale. Supposing the photocell has taken a measurement and says there's 5 units here, well, as we've got 8 binary digits here, it's a 1, no 2s, and a 4, making 5. And again, for a 7, it's 1 and a 2 and a 4, adding up to 7. And so instead of trying to send these amplitudes, as one does in normal radio, one could send indeed these strings of either noughts and ones, like that, and the instrument at the far end could receive them, process them, and effectively draws these lines for you and will draw the envelope like that. And that is the principle of what is now called digital signalling. Its value is that you've only got to send impulses or not send impulses. And so you don't have to depend on amplitude. The price you pay is you have to send a lot more impulses per second than you would if you did it this way. But this turns out to have enormous advantages, and so digital processing has become important for signalling, and it's particularly valuable because, as we've seen, these are signals which computers like. Now, all our own signals up and down through our limbs are done by a system, not necessarily of digital signalling, but at least of pulses. The more intense the sensation, the greater the rate of pulses travel. And this is not from a human being, it is from a moth. In fact, it's from the antennae of a moth, and the physiologists are at least as skilled as the physicists in doing these micro-manipulations. They can actually tap in to the nerves from the antennae of moths, and this is a male moth, and he's being effectively, through his antennae, being wafted traces of the kind of scent which is emitted by the female moth, and you can see as the strength of the scent is increased, it's the number of pulses sent down the nerves to the insect's decoding brain which increases. And so, as it turns out, all animal signalling is done rather by this system. So, if we can now look at the next slide, we can come to the technique which I want to demonstrate to you after we have seen some examples of processing. As I said before, we already seen them without perhaps realizing quite what was involved. But the pictures that we saw on those 2 occasions were in fact stored in a computer, decoded effectively into a binary system and stored in a computer. Now, the firm that makes all that picture processing equipment, whose benefits we have received during these lectures, is a firm, Microconsultants, and Mr. Martin Trump, a director of the firm, is here. Having been a boy himself here many years ago, he said, and so he was only too willing to participate. And if Mr. Trump will come out and operate the computer, there isn't enough time to demonstrate to you many of its powers, and also it's only working in black and white. But what we're going to do is to get the camera number 3, I think it is, to look once again at the famous picture of the Royal Institution. And the first example that I want you to look at is the effect of adding what we call noise to that picture. It can be from any form. We call it noise, although it's strictly speaking not noise, but a large number of spurious signals coming in, and so one loses the detail in the picture. And this corresponds very much with trying to take an observation in the presence of large numbers of disturbances. And we can show the effect of integrating over a whole number of observations, because if that picture is stored over a period of 10 seconds, each successive trace, the real objects in the picture will always be in the same place. The noise will come up all over the place from one frame to another, and therefore can gradually be averaged out. And if we can average out over, let us say, a period of 10 seconds, if you can see it all on the monitor, and you can see now the noise is spoiling the detail. Now there will be a blank. We're not losing the picture completely, but it's gradually being built up through the noise. And you can see, as a result of storing lots of noisy pictures, the ultimate picture again appears in detail. A very pictorial example, again, of the thesis I've been saying all along here, that accuracy costs time. And as one is prepared to spend the time, one can make more accurate observations, and this picture and its noise has demonstrated it. One of the other things you can do is a sidelight perhaps on how an artist works. Because if we take part of that picture and bring it up in scale, then like that, we can ask the computer not to reproduce the intensities like that, but to tell us where there are sharp changes in intensity. So that if you went from white to black, the computer would take no notice so long as it was going across white. It'd take no notice once it goes across black. But on the interface between the black and the white, you say something's happening, and it will bring up a bright line. And so if we now proceed to ask the computer to do that for us, down here gradually through the picture, you'll see the picture gradually converting from what was an ordinary picture. And it's a particular point is to look at the edges of the table, look at the glint on Mr. Coates's hair, which is just going to come, you see. And quite a lot of the detail is disappearing, but you see the sharp edges are beginning to appear. Look at the table now particularly. You see a lot of the detail has disappeared, but the things which we're interested in and which an artist doing a sketch will very often do is in fact those details are remaining. The outlines, it's drawing the outlines for us. Now that is rather, as it were, a chalk drawing on a dark background, and with a press of the switch it can go the other way, and we've now got almost the equivalent of a pencil sketch on ordinary white paper. Well, these are very simple examples of what this system will do. One can use that particular technique in order to spot outlines of shadowy things under microscopes, for counting particles and estimating the area of cells and so forth. And the elaborate equipment which is used on large scale by television companies, we have seen these most dramatic demonstrations of in the earlier lectures. The similar equipment has been used for processing. Thank you very much, Mr. Trump. Similar have been used for processing those most impressive pictures coming back from spacecraft, where at any one picture, if you looked at it straight away, you would see almost nothing. But thanks to all this computer help, pictures can be made readily intelligible. The third field of technology on this kind of scale I want to talk about is not quite the microchip itself, although microchips are very much involved, but in the possibility of storing information by a technique which one could see might happen. In fact, when was it? It was 1970. I had the European Commission on Human Rights asked me to look into for them the matters prospective threats of technology to privacy. That included things like the eavesdropper we saw here the other day, but also one of the main areas of concern was the possibility of information being stored on a widespread scale, and information about individuals that they might not have wanted stored in that way. And so the creation of data banks, as they were called, was a matter of some apprehension. And so when I was looking into those possibilities, I happened to read of an idea in an American patent, I think it was, that one might be able to store an enormous amount of information if one took a thin sheet and punched tiny holes in it with a laser. And I just wrote it out as a theoretical possibility that perhaps one day one might be able to do this, making holes of about a micron diameter. And here we are, only 11 years later, and already the technology, which was then, well, just a vain hope almost, it seemed, is with us to a stage that I now want to demonstrate. In particular, this example is being developed by the Philips company in Eindhoven, and partly because, in a way, despite the fact that in many senses we're all competitors, we're all brothers in this striving for precision, partly from that fact and partly from the fact that the directors of the firm, some of them were working in the Dutch resistance and knew of me in an entirely another connection, that when I wrote to them, asked if they could send some of their work over here, they not only very readily obliged, but they've actually had an engineer on standby through the year in Eindhoven in case anything needed to be corrected. In fact, everything so far has worked extremely well. And it's in here. And what it is a video disc. It records, in this case, a television program, and it will record 36 minutes of a complete television program, coded in the way with all its color signals, all its sound signals, everything in the way that we were talking about. It is actually already, you see, better than what I thought might be possible 10 years ago. The holes, effectively, it is holes in a disc like a gramophone record, but whereas a long playing record, what will last half an hour, I forget what the distance between the grooves are, but here the distance between what corresponds to the grooves, the tracks, are only 1.6 microns apart. 1.6 microns would be, what, about a 15th of an inch? Yes, about a 15,000th of an inch apart. The holes themselves are 0.4 microns in diameter. In other words, less than 1/50,000th of an inch across. And when we tried to look at them in the discs we have under the microscope, we couldn't see them. The resolution with an optical microscope was not good enough. Under an electron microscope, one can see them. And when I tell you that if that disc, which is about that diameter, we'll have a look at it in a minute, were unwound, the track would stretch from here roughly to Windsor Castle. There's all that much on a disk this size. The original disks are made by using a laser and putting the laser light through here. The information now has been coded on something like a binary scale. The laser is alternately flashed on and off as the disk here rotates, and the beam of light from the laser, which is focused on the disk, hardens what we call the photoresist locally, and so when the disk is suitably treated, one gets raised pimples, tiny pimples, about 0.4 microns across, on the disk if the light was on. So in this way, one builds up a disk, all these grooves 1.6 microns apart, the pimples perhaps 0.4 of a micron, and we then have a master disk. And from that point onwards, if the master's been made, it's really just like pressing a gramophone record into transparent material, and one gets, of course, a disk with lots of tiny pits in it. And those pits are so narrow that when you look at them with a second laser now, the analyzing laser, the light coming back has had to be, because this makes use of the fact that light does not travel in straight lines, the light coming back from the pit is already diffracted, and there's a photocell at the side here, beside the laser, that picks up the diffracted light and tells you, therefore, whether there's a pit there or not. On the plain surface of the disk, the light just comes straight back. But where there's a pit, the light goes down a little bit, comes out again as Wirthroth slit, and fans out and is picked up by photocels. An actual section of the photomicrograph of the disk, you see how beautifully these regular these holes are, and you see all the respective tracks. And to give you some idea, the prize, of course, is being able to sell gramophone records or something like it in a record player and demonstrate and play back the information in the form of pictures. That is the actual reading head on the laser itself. And if we can see now the output of this device, there we are. And you can see now at any time I can stop it, freeze it, like that. And we can make it go, make it go forward slowly. And the marvelous thing is that you can get anywhere on this disk you please, and you can make it go forward slowly if you wish to, like that, frame by frame, as you see, and we can speed it up, and all this information is recorded. We'll stop it, we'll make it go backwards if we want to, like that. All that information in those pictures and the sound that accompanies them, you'll see. It frees on a single frame, so let us go forward. We'll go forward at a slightly more reasonable speed now. Here we are, we can make them gallop like that, and in, up come the next lot, like that, and there we are. You'll see complete pictures. Well, we'll stop them again, shall we? We'll go backwards. Here like that, you'll see. There we are. Where would we like them stopped? I don't know. Yes, there we are, like that. Well, all that, you see, in fact, a whole television program of 36 minutes would go onto one side of the disk. And now I'd like to stop the thing just to show you and it won't allow me to open it for a little while until the whole thing is has stopped, because one might otherwise do damage to the disk. We'll have to wait for a moment. Here we are, like that. And here is the disk itself. You can see it gives the most marvelous diffraction pattern all over the place, because it is, in fact, a very fine diffraction grating. Here we are, like that, you see. I don't know whether those of you can see it directly like this. And this is the one form of the video disc. Now, there we have it for, now I best for safety put it back here. There for safety it is, and this is the form in which it can be used for recording whole films, television programs and so forth. And it's entirely mechanical, as it were. The information is in the form of these tiny pits on that disc. Well, you could imagine the amount of technology that's gone into this and into a beautifully simple apparatus like that, where everything can be positioned and followed with an accuracy of something of the order of 1/10 of a micron over the whole of that disc. And you can see the potentiality for recording, because instead of using it for recording pictures, one recorded it for storing words. A disc that size would hold the equivalent of 500,000 printed pages, all in the one disc, like that. So there is one of the triumphs of modern technology. We're coming very close to the end of these lectures. If I can have the next slide, this indicates well, there are two things to show, really. There's this Christmas card that I received from the University of Glasgow, if it can be seen. And you can see, I hope, it's Snoopy. Is that as well placed as... Yes, yes, the thing here is just the bow, ornamental bow of the Christmas card. And to give you some idea of the scale in which our colleagues in the Electronic and Electrical Engineering Department at Glasgow can draw things with these techniques which they are building up for the next stage in microcircuitry. The lines along the base here are 1 micron, and the width of the actual line, which is drawn, is about, was it 2/millionths or so of a centimetre? That's right. And possibly in a few years' time, microcircuits could be fabricated by these techniques. This is a more difficult thing to do, really, than this slide, because this is actually done as for microcircuits. But the ultimate that I know in recording at the moment is by the University of Cornell, which has what's known as a submicron department. And here you see they've actually been able to write in letters which are only 2 10/millionths of a centimetre in the actual writing width. And we're getting to the stage, this is on a sodium chloride crystal, a much easier job than that, basically, but it is in fact about 10 times smaller. And we're now getting to the stage, you see, where by comparison, here is a tobacco mosaic virus with its molecules there, and we are getting very near the stage where the fact that atoms are involved, we won't be able to go very much further. So that, at the moment, I know is the ultimate in, as it were, this microscopic work. Had there been more time, when we certainly look at the next slide, I would have liked to talk to you about some of the times when very precise measurements have had an enormous effect. How many of you have heard of the conservation of energy? And how many of you know that it was Joule who formulated it? Well, Joule's first paper on the conservation of energy was rejected by the Royal Society. The reason it was rejected, as Kelvin said, and Wheatstone was one of the main rejectors, incidentally, was that Joule had nothing but hundredths of a degree to prove his case by. But it was Joule's ability to use good thermometers and measure to a hundredth of a degree that in fact established the great principle of conservation of energy. And in our own time, or certainly my time, history to you now, the painstaking work of Aston in Cambridge, which showed that, and he measured atomic masses relatively to 1 part in 10,000, the fact that the atoms in the middle of the periodic table, their nuclei were so much lighter than they ought to be, in a very small amount, and mass had disappeared, energy must have disappeared with it, and that therefore one ought to be able to get energy out if you could fuse atoms, the light atoms, like that, or split the heavy atoms like that. The whole of atomic energy came out of those very precise measurements. Well, that's all I want to say about measurement itself. I did ask in the literature, can we carry measurement too far? Well, in a sense, we can. We've certainly got to be very careful because, as we've seen, the results of measurements have been able to do so many things that were so difficult before that they made various kinds of work actually superfluous. We can create enormous social problems if we're not careful, and they've got to be anticipated in advance. And in that sense, measurement can be carried too far, though, as always, and we've seen that it can be used either for good purposes in peace or bad purposes in war, but the same is true of, as Francis Bacon pointed out at the beginning of the scientific revolution, the same can be true of everything you can think of, from beauty to knives. And so the responsibility of the way it's used is in the hands of us all. But there is another sense in which measurement can be carried too far, partly because it has been so successful that the impression is often given that unless you can measure something, you're not a scientist. It started with Kelvin. It may be true, but the result has been that everyone who wishes to claim he's a scientist pretends he can measure things. And the difference is, and why it succeeded in physics was we're dealing with things which are really basically very simple. In things like economics or intelligence assessment, the factors are so complicated that it is very dangerous to try to put numbers on them. And numbers can be very misleading. A policeman, for example, who makes very few arrests may seem to be a worse policeman than one who makes a lot. But on the other hand, it may be such a good policeman that people don't commit the crimes. And so one's got to be terribly careful in judging on simple numbers unless you really know the factors. And now, just to conclude, because the Phillips system, when I read of it, reminded me of one of the things of my boyhood. And here is a sample from the Science Museum that they very kindly let us have of what is called a symphonion or polyphone. And I would like to, as it were, to play out with this record. It's all beautifully mechanical. The holes in the disc pluck the reeds, as you can see, and if I can get the thing on properly, which I have so far failed to do, well, you do it, because I would like, in absolute conclusion, before the thing starts, to say thank you to all of you for being such a splendid audience.